this video, I'll talk about the solution for the assignment this week. And so let's start. Okay, the first one. So the switch has been open for a long time before t equal. Well, there's no switch. I forgot to put the switch here. And it's closed at t equals 0. Or maybe you can regard it, we have a intrinsic switch inside the source or in series with it. And it's closed as t equals 0. So assume that C, L, R are like this. Or equivalently, if you just ignore the switch, you can regard Vs to be 3 exponential to 4t times the step function. Ut is the unit step function, which means it is 1 for t is larger than or equal to 0, and 0 for t is smaller than 0. So this is called a step function or unit step function. Unit step function. Okay, so so we would like to find the expression for I for t is larger or equal to 0. And actually we in the first step we should write an ODE describing this circuit. So actually we can use the KCL to write equation at this node, So there are 2 current going in and 1 current going out, the current which is I. So in this case, for this current, it would be something like, well, actually, if you're familiar with enough, this voltage will be, this voltage here would be L di dt. L di dt. Actually, we can say it VL, but as long as we have too many variables, then we'll feel confused to solve them, because we'll tend to write some formula which are dependent, and then we cannot eliminate the variable. So it would be better for us to eliminate the variable as long as we can, which means that I is an important variable, so we can express the voltage at this node, or the node voltage here, in terms of I and L. So and of course, the node voltage here is Vs. There's no doubt. So in this case, the current going through the resistor will be Vs minus L di dt over R. Okay, so the next, this current in terms of V will be C dV dt. Which is quite trivial for a capacitor. So the next one, these 2 currents, we add them together, will be equal to this current I. And actually we can just try to simplify it a bit. Well, it is not actually simplifying, but we try to reallocate some of the term. We have this term moving to the right side, this term also moving to the right side, so it will become plus L over R di dt. Also, we have this term, so we have plus I equals to Vs over R. So this is the first equation we can get. And the next one is we can use the KVL. So this is the KCL here. And the next we can use the KVL. For the outer loop, something like this. For the outer loop. Okay. So in this case, this is Vs. We may start from this node and then we go to here. So it is Vs. And then the voltage go up here and then will start to go down by V. So it equals to V. And then this one plus LDI dt. Okay. So in this case, we have we can write it as V equals to Vs minus L di dt. So we just move this term to the left hand side. So this is the second equation that we can get. So next we try to eliminate some of the variable. So actually for the first equation, let me see. For the second equation, we can take the derivative. Well, for this equation, we can take the derivative of the second equation, so that it will become dv dt equals dvs dt minus L second derivative of I with respect to time. And then we can see that we have C here, so we multiply this one by C, so we have an equation like this, and then we can add 1 and 3 together, so we add 1 and 3 together, so that this term and this term are cancelled. And then on the left hand side, we have L over R di dt plus I, so equals to Vs over R. So we have this term, and this term. And then next, this is already cancelled. So, and we also have this one. So we have C dvs dt. And this one on the right hand side, in terms of I, so we move it to the left hand side. So it becomes LC, second derivative of I, something like this. Then we can just divide LC on both sides. So then we can just divide LC on both sides so that we have the normalized second order coefficient. And then this one, so we have L over LC, so it become 1 over RC di dt, and then plus 1 over LC I equals Vs over RLC plus 1 over L dVs dt. Okay, so that we have a ODE describing the circuit in terms of I and RLC and also Vs. Then we can substitute all the values or the expression in it. So we will have second derivative of I plus 1 over RC. So we have R is 2, C is 1 over 16. So multiply together 1 over 8, 1 over A, and then in the denominator, so it becomes 8 di dt plus So next we have 1 over LC, and we have L is 1, C is 1 over 16. So LC is 1 over 16, and in the denominator, so it is plus 16 I. Okay, so on the right hand side, we have RLC multiplied together. RLC, R times L times C, 2 times 1 times 1 over 16, which is 1 over 8. So here it is, so we have 8, and the Vs is 3 times exponential to 3 times minus exponential to minus 40. So we have 3 times exponential to minus 40, and then 1 over L is 1 over L is 1 over L is 1. 1 over L is 1, and then the first derivative of this one, which is this one, so we have minus 12 exponential to minus 40. So we have 24 minus 12, which is 12 exponential to minus 40. Okay, so we will try to solve this second order constant coefficient ODE, and actually we will have the initial condition, which is I of 0 plus, also di dt 0 plus, but we can find it later on. So try to solve this. We'll try to get the form of the solution first. So first of all, we try to solve for the homogeneous solution, which is, we can write it as s squared plus 8s plus 16 equals to 0. So s is minus 4, which means that, and actually this repeated real roots, which means that the homogeneous solution IC would be a plus bt times exponential to minus 4t, like this. This is a homogeneous solution. And actually, we have the external force, something like this, which is exponential to minus 4t, which is also repeated with this one. So in this case, we should assume our particular solution to be, maybe you should not use c, we can use d, exponential to minus 4t, but we actually need to multiply by t squared because we have constant, the first order, the 0 order term and first order term. So this one is pushed to the second order. So IP would be like this, and then we can substitute IP into plug it into this equation. So we take the second order derivative, which will be 16d second order derivative, 16 order d t square exponential to minus 4t. So this is the second derivative of this one, and then we need to have 2 times the first derivative of this one times the first derivative of this one. So it will become 2 times minus 4, which is minus 8 dt exponential to minus 4t. And then we have second order derivative of this one, which will be 2, which will be nothing but a 2. So it is 2d exponential to minus 4t. So this is the first term, and then the second one will be plus 8 times. First derivative of this one is 2t, so totally 16 dt exponential to minus 4t. And then 2d times the first derivative of this term, and then times this term, so it will be 2 times minus 4 is so it should be the first derivative of this term is minus 4, and then we have multiplied by 8, so it is minus 32 dt square exponential to minus 4t. So we have the second term, and then plus 16 times IP, which is dt square exponential to minus 4t. So this is the left hand side, and for the right hand side it will be equal to this one, equal to 12 exponential to minus 4t. So we can note that here we have 16 dt square minus 32 dt square. So this term can be cancelled, And also, wait, this term should be minus 16. This term should be minus 16 because it should be 2 times. Oh yeah, this term should be 2 times the first derivative of this one and the first derivative of this one. So it should be this one should be 16 rather than 8. So in this case, we have this is minus 16 dt plus 16 dt. So the remaining term is this one. Remaining term is this one. So we have 2d equals to 12, and thus d equals to 6. D equals to 6. In this case, we have I equals to IC plus IP, which is equal to A plus BT exponential to minus 4t plus 6t squared exponential to minus 4t. So next, we need to determine the initial value. Actually, at the very beginning, the switch here should be open. The switch here is open. The switch here is open, which means that there shouldn't be any current going through here, which means that I0 plus should be equal to I0 minus, which is 0. And for the di0 plus dt, we can actually calculate by VL 0 plus, which will be equals to VS 0 plus minus V 0 plus. And VS 0 plus, we can check it here. Vs is actually this one. So we substitute 0 plus into this expression, so that it is 3. It is 3. It is 3 minus, and the voltage of the capacitor should be continuous. So it will become 3 times 3, actually 3 volt. And in this case, we can use VL equals L di dt to determine the initial condition for di dt 0. So di 0 plus dt should be equals to 1 over L VL 0 plus. And L is actually 1 Henry. So 1, and then VL 0 plus is 3 volt. So 3. So which is actually 3A over S. So this is the 3A over S. So we have the initial condition. Then we can determine A and B. So I0 should be equals to A plus BT, and we substitute T equals to 0. So B times 0 is 0. So, and this one is 1, this one is 1. And this one is 0 because we have T here. So it is 0. So we have A equals to 0. Then I is actually BT exponential to minus 4t plus 6t squared exponential to minus 4t. And then we would like to calculate the first derivative of I. So it will be b exponential to minus 4t. And then the first derivative of this one, which is minus 4b t exponential to minus 4t. And then the first derivative of this one, which is plus 12t exponential to minus 4t, and then 6 times minus 4, which is minus 24 t squared exponential to minus 4t. And then we substitute I equals to 0 in this expression. So that this one is b, this one is 0, this one is 0, this one is 0, because we have t here. So any number multiplied by 0. Any finite number multiplied by 0 will be 0. So it is b is actually 3. So the final answer will become I of t is 3t plus 6t squared multiplied by exponential to minus 4t a. Well, actually, whether you factor out 3t is not very important. Actually, you can write it as 3t plus 1 plus 2t, but 1 plus 2t, but actually you can write it like this, it's okay. And this one is also good. So this is the solution for the first one, and then we go to the second one. Okay, for the second one, okay, we can actually use the superposition principle to find the solution of this one. Actually, we have two sources, so that we can just switch on one. The first one is we can just switch on this one, so it is 10 cosine 4t, and then this is 4 ohm, this is 2 ohm, and then this is an inductor. So if we like this, we just short connected this one. So originally this is 8 volt. So we can regard it as a 0 volt here, so that it is short connected like this. And then for the inductor, the phasor or the impedance of the inductor should be j omega L, and then here omega is 4, so that it is J4 ohm. Okay. So in this case, we can calculate the phasor I at this path, which is I equals to this is 10 over 4 plus 2 parallel with J4. This is 2, this is J4, they are in parallel. Because this no connect together, this no connect together. So this 2 ohm and J4 ohm are parallel. So in this case, we have 4 plus 2 times J4 over 2 plus J4. And then we can just have some algebraic calculation. It will become 50 over 20 plus A plus J4, which is 80, 20 plus 28 plus J4. And then finally it will become 25 over 14.14 exponential to J times 0.142. So this is in radian. This is in radian. Actually, you can simply converting this. So actually, if you have a complex number, a plus jb like this, you can actually write it as r exponential to j theta. R is actually a squared plus b squared, and then take the square root, which is the modulus of the complex number. And then theta will be arctangent b over a, or this one, or arctangent pi of b over a plus pi. It depends on which quadrant it is. Suppose your arctangent has a range in the first and fourth quadrant, then it is okay. And if your complex number is here, then you should add a pi here. You should add a pi. Which means that for this case, this is a smaller than 0, a smaller than 0, b larger than 0, and this one, a smaller than 0, b smaller than 0. Then for this second and third quadrant, you need to add the pi to this one. And actually this is in radian, so we have 14.14 times exponential to j 0.142, and finally it will become 25 divided by 14.14, which is 1.06 exponential to j minus j 0.142. So next step is to find the IO1 here. The phasor of IO1 will be, we can see it like this. I is here, so that's so this is, so we already get I. So the voltage here will be 10 minus 4I, and thus IO1 will be nothing but 10 minus 4I over J4. So this is IO1 equals to this one, and which is actually, you can calculate it to be 3 plus j over J4, and finally it will become 1 minus J3 over 4. And then if you convert it into polar form, which will become 0.790 exponential to minus J 1.249. Okay, so this is the this is a phasor of I01, and if we convert it back to the time domain, I01 will be 0.79 cosine 40 with the same frequency, but the phase will be like this, which is minus 1.249 A. But we have not done yet because we only calculate one of the source. For the second case, we need to calculate another source. We need to switch off this one. But in this case, it will be very simple because we actually switch off the left hand side voltage source, and this is 4 ohm, and the right hand side it is 2 ohm, and then we have inductor, and this one is 8 volts. 8 volts. So in this case, what is the frequency of this one? Actually, omega is 0. Omega is 0 for a DC source. So in this case, we have J times omega is 0 times 1. Okay, so it will be 0. So it is short circuit. And in this case, 0 ohm parallel with 4 ohm, and then it will become something like this, 8, and then 2 ohm finally become this. And then there will be no current going through that path, no current going that path. And this is actually I02. So I02 is A over 2, which is 4, 4A. So this phasor 4A, and actually I02 is also 4A because the frequency is 0, so 4A. So finally I0 will be I01 plus I02. So I01 is here 0.79 cosine 40 minus 1.249 plus 4A, and this is the answer. Okay, so this is the solution for this assignment. So we can find the IT for the first one. We can find IT using the potential method to write an ODE and solve IT. And for this one, we have if we have sinusoidal source or DC source, and if you would like to calculate the steady state, which means that we can regard it which means that for steady state we assume that the homogeneous solution will tend to 0. For any stable system, the homogeneous solution will tend to 0 for sufficient long time. So sometimes we can just ignore it. And we only care about the steady state response. Actually, you can also write a first order ODE in terms of I0 with the source 8 volt and 10 cosine 40 volt, and then you can solve the ODE And actually, if you just assume the homogeneous solution to be 0, and then you should be able to get the same result like this. So I think that's all for this assignment, and if you have any question, please let me know, and I'll see you next time.